Okay, so in the next couple of minutes, we'll look at handwriting recognition as one example for computer vision. And I'm sure everyone can imagine what handwriting recognition is about, and many of you probably have used it in the past. So whenever we have a document or something that a person wrote, and we want the computer to recognize what the digits are or what the letters are from handwriting, that's what we're talking about here. So we want to have computers understand what a human is writing, or predict what the letters are based on the information, the image that we're giving the computer. So this is something which allows us to automate many tasks. So for example, if we have a written letter and we want to translate that into a text document that we can store and search, that would be one application for handwriting recognition. So let's see in the next couple of minutes how we can model this problem. So how can we actually give a computer the information about a handwritten digit, and what can the computer then do with it in order to predict the correct answer, which is the label or the digit that is actually being written by the person. So we'll look at computer vision briefly, and then mainly we'll look at what image representation means for computers. So how do we represent images so we can have machines learn from that data? It's not that obvious for images. I think it's much more obvious for the iris data set, for example, that we used last time, where we have a set of features, like these 4 different numbers for each flower, and then we have a label, which is the type of flower. And so the data here is straightforward, and we can imagine, okay, this is what we usually put in a spreadsheet, and we can feed this to a machine learning algorithm, and we can basically imagine how that works. But for images, I think we need to take one more step and understand what a computer actually sees when we give it an image, and then we might get a better understanding of how that works. So let's first have a few words about computer vision in general, and this is from a book that I recommend if you're interested in artificial intelligence in the broader sense, and an analysis how it impacts business processes and the economy in a broader sense. So this is not a technical book. It's a I would say a book focused on economics, and it's very interesting. It's called The Simple Economics of Artificial Intelligence, and this is an image taken from there, and it shows you how machines progressed and got better at image classification, which is basically what we're talking about here. So image classification, there's a famous challenge that is taking place every year, where different algorithms, so different models basically see the same set of images, and they should recognize or predict the label correctly, what is being shown in that image. And so they have a competition, and whoever has the best accuracy, so the smallest error rate in terms of error rate, wins the competition. And so this is the chart for every year of the error rates that different algorithms, or the winning algorithm has achieved. So in 2010, as you can see, that was before the deep learning revolution. So the deep learning revolution basically started in 2011 or 12. So when we see this downward slope, and by that we mean the great success of applying neural networks with enough computing power and enough data for specific tasks, and one of them being computer vision. And so we were back in 2010 at around, I don't know what that is, 28% error rate. That's quite high. So you look at images, and basically the computer guesses 60% or 70% of the time what's in the image, or it predicts correctly, but it has a huge error rate. And this error rate has dropped significantly. And if you look at the recent years, which is already quite old, I'm guessing we are already further below. But in 2017, it was already below 5 error rate. I think this is about 2.5, and in 2015 already we got below the 5% benchmark, which is the human benchmark. So even if humans look at images and try to predict what's in it or classify these images, they have an error rate about 5%, and that's for various reasons. So one of them being that even if we see like a certain kind of dog in an image, we can say it's a dog, but we can't really precisely say what kind of dog it is. That might be a lack of knowledge, or it might be a lack of, so we don't really recognize the dog correctly. This is just an example, but we do make mistakes, and it's about 5% in this particular challenge. So what machines achieved is to go below this human benchmark and being able to more precisely predict what's in an image than humans can do. And this is especially true when we look at images that are not something we see in our everyday lives. So for example, a dog in a garden we might see frequently, but looking at CAT scan images, this is not something we frequently do. So this is only something that a trained expert would do. And even trained experts, they get tired and they make mistakes and so forth. They have all these biases that humans have. And when we use a machine for this very same task, we see that they outperform humans when they are trained properly and when they have a very specific task that they should solve. And so this is a chart that shows that we have a very good that machines are very good at predicting or classifying images, and this of course leads to machines being also used instead of humans. So for example, in medicine, in medical analysis, where we have doctors and machines working side by side, but also this enables things like autonomous driving, where we rely on image classification or real-time video classification, which is just a special case of image classification. So we have use cases where we need an even better error rate. So even for autonomous driving, I think that 1% error rate is not good enough. So we need much better. But this is just this is the result from a very broad set of images that the machine should be able to classify. If you have a very specific task or application, we might even get better results. And handwriting recognition is one of them. So that's a very specific and much narrower application. So we have only a limited set of characters that we want to recognize, and not just the whole world and its objects in it. So this is just to show you how good machines have become over the years in computer vision in general. So this image is to show you what actually computers see when they see an image. So this is a cat, obviously, for us humans. It's very easy to recognize. We don't even need to think about this. So we just look at it and we immediately have a cat in our head. But for computers, this is totally different. So computers do not see a cat in that image. They don't even see the colors or the other things like the trees that we see in the background. Instead, what they see is this array of numbers that you see on the right side. So basically, and we talked about this when we introduced the RGB code. And the RGB code is basically a code to represent colors. And when we can represent colors, we can represent an image as a list of pixels that have a certain color. So this is what is being depicted here. So every number here could represent a certain color and a certain pixel. And this could then be a very large list of basically numbers that represent colors that make up this image. And this is what the computer sees. So there's only this large array, this large vector of numbers. And then the task seems quite hard. So the task is to have these numbers being fed to a computer, and the computer should predict whether or what's in an image that is represented by these numbers. So for humans, that's impossible. We would rather see actually the cat in an image, but the computer needs to have a representation in zeros and ones. So ultimately, every image is going to be a large sequence of zeros and ones. And These are just decimal numbers for convenience, so we can read it better, but the computer sees zeros and ones in a large sequence for every image that we feed it. So the problem then gets reduced or transformed into a problem of a large array of zeros and ones and predicting something based on this very large pattern or sequence of numbers. So for the handwriting recognition, the question becomes, can computers learn to recognize digits like these? And when we know that, so this is examples for handwritten digits. And again, we as humans, we can probably directly recognize what these digits are. It's 5041. But for computers, again, the problem is much harder, or it's not obvious because they only see numbers. And how can we then represent these digits as numbers? Well, in the same manner as before, we use a large array or a large vector of numbers, and we need some way to represent different colors in these images. And then we can represent basically each of these digits as a list of numbers. And this is how the last digit, which is the 1, could be represented, in this case, in a matrix. And the matrix, as you can see, mostly contains zeros, and that would be white. So in this case, if we have a white area, the white area here, you can see it's all represented as zeros. And then if we have a black and white image, which is often the case when we have text documents scanned, and we don't really care about color, then we could have a grayscale image, and then we could represent each level of gray with a different number between 0 and 1. So 0 would be white, and then 0.6 would be a little bit darker, but 0.8 would be even darker, and 1 would then be black. So this would be one way how we could represent an image. And as we will see later in our example data set, we actually apply this kind of coding, but instead of having a decimal number between 0 and 1, we will have a number between 0 and 255, because that's the size of 1 byte, and we will have 1 byte to represent our grayscale. So 255 would then be black, and 0 would be white, and everything in between is just a grayscale. So our data set, and now we are talking about a specific data set called the MNIST data set. That's a very popular data set that is publicly available and which is often used to benchmark handwriting recognition algorithms. And it's also a good data set to introduce the topic and to play around with it ourselves. So what does the data set look like? So first of all, it's a lot of images. Here it says 55,000. It's I think the latest version is 60,000 images of handwritten digits from different people, and these images are represented as vectors of numbers, and they are 28 by 28 pixels, and this makes it 784 numbers for one image. So 28 by 28 times 28 is 784, and so what we actually have is a vector of 784 numbers, and we have 55,000 of them, or depending on the version we use, 60,000 of them. So this is what the data set looks like. This is what we call the features. So now when you think about the iris data set that we used last time, there we had 4 features, and here we have 784 features. So it's much more features, 1 for each pixel, and the value of a feature is going to be the information of the gray scale of that image, of that pixel. So this is the features, and then the labels are, again, for each of those images, we also have the label because we're talking about supervised learning, and the label is a digit between 0 and 9. So we have only the digits from 0 to 9 that we want to recognize. And so we have 10 different labels. And again, for every image, for every number vector with 784 features, we have one of those labels, which is the correct label. And this is the label part of the data set. So we have the features and we have the labels. And then we do some training, and that is what we're going to do hands-on after we looked at this. So the training basically involves showing exactly the features and the labels to a machine learning algorithm, and the machine learning algorithm is then trying to learn the patterns of the different digits. So when it sees a 1, and it will predict, I don't know, when we start in a very early stage of the training process, it will be terrible at predicting because it's basically random. It will simply say, okay, this could be a 4, right? And then we tell it, no, this was not a 4, this was a 1. And what happens then is it will, based on the response that it gets, that the label was actually a 1 and it was incorrect, it will try to adjust its internal model. And what that means, we'll look at when we talk about machine learning algorithms and models in the next session. So we'll look at 1 or 2 examples and how could they now learn this kind of thing. But basically what they do is they look at, okay, my prediction was that, okay, this was the correct answer, so I was wrong. So what would I need to change internally? And there are a lot of parameters in every model that the model can learn. So what do I need to change so that next time I see the very same pattern, it's more likely that I will predict the right thing. So this is the question that the machine or the training algorithm must solve. And there are many different algorithms, different models that can learn these kind of things gradually. So they usually learn in very gradual steps. So they might need to see the same data over and over again to really arrive at a state where they will be able to correctly predict the 1 when they're done training. So this is the training, and once we're done with training, it might have learned something like this. So this is just 28 by 28 pixels, and this is called a filter. We can represent this as the red parts that say, okay, whenever, so we now feed it an image and we apply this filter, and the filter simply says, okay, for a pixel in this area, so a dark pixel in the red areas that you see in the middle and a little bit around, it's a very low probability, so it will decrease the probability that this is a 0. And if there are pixels in the blue area, that's what it has learned from the data, it increases the probability that this is a 0. This is one way what a model could have learned. So it can learn which pixels increase and which pixels decrease the probability. And then it will simply go through each pixel and add up the probabilities 1 by 1, and it will arrive at a number between 0 and 1. And this it will do for all of its possible outcomes. And then it will decide, okay, which is the one with the highest value, and this will be the prediction then. And you can see, if you look real close, this resembles a little bit of a 1. So if you have the pixels in the middle and here, it's more likely to be a 1, and here it will decrease the likelihood that it's a 1. And so you can see that this is a little bit looking like a 2, but in the middle it has learned there shouldn't be pixels. This looks a little bit like a 3. So you can actually imagine how these filters work when you look at this image. And this is one way how you could imagine what a model could have learned. When we think in terms of these filters, and we simply run a new image that we should recognize through every one of these filters and determine what the number is going to be, and then we have one number for each filter. And this is what, for example, a neural network could do. So we put in the 5. For us, it's obvious it's a 5. So we feed it these 28 by 28 pixels, and then the neural network has learned some parameters and weights that are going to change whatever is coming out at the end, and then it might arrive at 91% confidence that this is a 5, but it might also have, I don't know, probably higher confidence than this that it's a 6, because 6 and 5, they actually look quite similar, and you can then look at the patterns it has learned. So they have actually similar areas, but it's good enough so that it can be distinguished. So this could be the output of a neural network that has learned these filters. And So then we can after we have done training, as we did with the iris data set, we can run through this network a number of test data, and the test data will then be it will also have a label, and then we can check if the network recognizes all the labels correctly and how high the error rate is. And that's basically the error rate that we have seen in the competition in the first chart. So whether it's, I don't know, 5% wrong, that means 5% of the time it doesn't recognize or predict the right label. And of course, we are going for as high as possible. So in the best case, we want to have 100%, which is impossible because we talk about statistical models and they will always have digits that they haven't, that they can predict correctly. Just by chance, just by probability, this will be the case, but we can achieve very high accuracy with handwriting recognition and image recognition in general.